welcome to our Baseload LNG technology options deployed in the US webinar. We're super excited. We are going to be doing a Q&A at the end, so if you have any questions throughout the webinar, there is a question box that you can drop those in throughout the whole webinar, and we'll get to those at the end. And I'm going to pass it over to Kendra.
Good morning, everyone. Welcome to the discussion on baseload LNG technology options deployed in the U.S. Oh, come on. Oh, goodness. Oh, no. For some reason, my computer has decided to freeze. There we go. All right. A bit of an introduction. I'm Kendra Snow McGregor. I have a bachelor's and master's degree in chemical engineering. I have over 29 years of experience in the oil and gas industry. I'm an experienced trainer. I'm also the technical director for oil and gas processing for PetroSkills. I started with the company back in 2008, and since 2011, I've been a full-time instructor and content developer. As far as our company, PetroSkills is now part of the Competency Alliance, which is also now a part of Relion. We do competency management consulting, training and development solutions, and we also provide software solutions. As far as the legal bit, just note that we will not be held liable for any investment decisions you decide to make as a result of the information that you receive in this webinar. So let's get started. What exactly is LNG? So let's take a poll because I'm curious to see what your thoughts are. All right, I think we ran that long enough. So notice which components are LNG. 7% said methane. Parker, am I showing this? I'm not sure if this is coming through on the screen.
Yes, everyone can see that.
Perfect. Thank you, ma'am. All right, 7% said methane only. 33% said methane and ethane. 7% said C1 through C3, and 53% said C1 through C4. Now, as far as the correct answer, notice LNG can be anything from C1 to C4. What actually sets your LNG composition is determined by the composition of the feed gas going into the plant. In terms of LNG, LNG is simply natural gas that has been cooled and liquefied to minus 162 C or minus 260 F. It is stored and shipped at atmospheric pressure. So essentially all those big LNG storage tanks and the LNG carriers that you see going across the ocean are full of boiling LNG at minus 260 F. We transport the LNG in specialized carriers, trucks, and ISO containers. To put this into perspective, 175,000 cubic meter ship, which is the most common carrier size today, contains about 3.6 billion standard cubic feet of gas. So it's a very efficient way to transport a lot of energy around the world. As far as the volume reduction, notice 600 to 1 volume reduction, and that's going from standard gas conditions to my LNG conditions. As far as our uses, we're primarily using the LNG as fuel for heating and power, but there's also other use cases, such as feedstock for chemical production. We also will use it for transportation fuel. Another, boy, I don't know why my computer is really locking up. I do apologize for the delay. Transportation fuel. So one of the hottest uses right now is for marine fuel to meet the CO2 carbon emissions. And we also use it as a heat source for manufacturing processes and furnaces. Now, as far as a brief history of LNG, let's take another poll because this one is actually a lot of fun. So let's see what you guys think. When was LNG first created? All right, I think I will show the results. Notice 0% said 1815, 33% said 1845, and shockingly enough, that group is actually correct. We first discovered LNG in 1845. 43% said 1942, and 24% said 1964. So as far as a brief history of LNG, come on. Notice Michael Faraday in 1845 discovered that natural gas could be liquefied. In 1873, our friends, the Germans, invented the first practical refrigeration compressor. In 1959, we had our first ocean voyage of LNG, and that was on the Methane Pioneer. On 1964, we had our first commercial LNG trade, and that was from Algeria to the UK and then to France. In 1969, we had our first LNG imports from Alaska to Japan. That was the first Conocophillips optimized Cascade plant. And then in 1970s, a number of countries started building import facilities simply because they did not have the natural gas that they needed to support their industry. So that included the USA, Europe, and a lot of Asian countries. In 2009, we had our US shale gas revolution, and really it was that revolution that enabled the US to become an LNG exporter. In 2016, the lower 48 has their first export of LNG cargo. That would be our friends at Sabine Pass at Cheniere. And 7 short years later, in 2023, the US becomes the world's largest LNG exporter. Come on. So everyone, I really do apologize about my computer. I don't know what is going on with this delay. It is just not responding to me. This gives you an idea of the growth that we're experiencing in the lower 48 in terms of our LNG export. You guys, this chart here covers not only the United States, but it also covers Canada and Mexico. But as far as our North American LNG exports, we're on track to double more, to more than double by 2029. And basically, the LNG projects that we currently have under construction is equivalent to 13.3 billion standard cubic feet per day, which is equivalent to 93 million tons per annum. As far as the locations of these facilities, notice in the lower 48, all of these LNG export facilities are really gathered in the Gulf of Mexico. And so, as you can imagine, that has put some significant pressure in terms of the labor market and other constraints as a result of all these facilities being located in the same general area. Now, let's talk briefly about the LNG value chain. As far as the LNG value chain, basically, it's a transport business. All we're doing is the LNG allows us to sell gas from locations with excess supply and reserves to nations that have inadequate energy supply. So buyers would be Japan, Korea, EU, Spain, China, etc. The US is the largest producer, and Japan and China and the EU right now are the largest consumers. Basically, this allows profit to be made by selling their gas into markets where the natural gas prices are higher. And this mode of transportation is significantly more flexible than pipeline gas. Now, this gives you an idea of the traditional integrated LNG value chain. And this is really how the industry got developed. And so back in the day when we very first, I mean, we went back to Algeria, basically a consortium of companies got together and they decided that they were going to build this project. And so they had to do the exploration, the licensing, the production. They had to build the liquefaction plant. They had to build the storage facility. They had to build all of the LNG carriers. And then their partners had to build the LNG receiving terminals, the regas, and the final distribution of the natural gas. Now, as far as the US, our market is significantly different in that we're selling pipeline gas. And so there is significantly less infrastructure required for our LNG facilities as compared to other locations around the world. The benefit of this is we have less infrastructure required. We have plentiful, cheap natural gas for now. And we also were able to build much more flexible contract structures than our competitors overseas. In terms of transportation efficiency, notice this slide is showing you the comparison between transportation by LNG, pipeline, GTL, or electricity. And so if you look at this example here, where I'm showing an LNG cargo going from, say, if we're going to go from Houston to Chicago, that's 940 air miles. If I wanted to send a cargo from Corpus Christi, CCL, over to the UK, notice that's 6,300 miles or 10,000 kilometers. The amount of LNG I still have sitting, or natural gas I still have sitting in that carrier, is roughly 90% of the molecules that I put into my plant. And so it's a very efficient manner of transportation. And notice the pipeline, there's a limit to how far economically it makes sense to do pipeline transportation. And that's simply because we need to burn the natural gas to keep the drivers for the compression going along the length of that pipeline. Now, as far as our primary advantages here in the US, the first thing is time to market. A number of our LNG export facilities were actually built as import terminals. And so those import terminals decided to build export terminals. And as a result, their LNG storage tanks are already built and on the ground. If you think about the infrastructure it takes to build an LNG storage tank, you're probably looking at 3 years. It's a massive project in and of itself and exceptionally expensive. So you're probably looking $20–30 million. We also have a much more competitive pricing and contracts. And right now we also have a very favorable regulatory environment. And so with those combinations, what you're seeing is we're witnessing a lot of additional export facilities turning to final investment decisions recently. Now, as far as our natural gas and LNG trade market, just to put the value chain into perspective, I think it's important to consider where we fit in the global energy demand. Global natural gas consumption provided roughly 25% of the world's energy needs in 2024. 27.6% of this natural gas was traded on the international market. 48% of that trade was via LNG. So it's a massive international global business. In 2024, global gas consumption hit a record high, increasing by 2.8%, or roughly 404 billion standard cubic feet a day. As far as the US and where we fit, we produce 26% of the global demand and we consume 22.4%. In 2024, we provided 12% of the total, our total production was sold as LNG. And so basically we sold roughly 12 billion standard cubic feet per day. In 2024, we produced roughly 100 billion standard cubic feet per day. In 2025, our LNG export facilities under construction is really quite sobering. You're looking at 13.3 billion standard cubic feet of additional export capacity coming online. And so put that together, that's essentially 25% of our 2024 natural gas production. And so there could be some implication in terms of our natural gas pricing in the United States as a result of the level of LNG export facility build out. Now, let's ground ourselves in the LNG trade. In 2024, the LNG trade was roughly 411 million tons, or metric tons, million tons. US supplied 88.4 million tons. That's 21% of the global trade. 53% of those molecules was exported to Europe, and 34% of our molecules went to Asia. Right now, our capacity is projected to be 181 million tons by 2029. As far as liquefaction capacity increases, in 2024, we brought 6.5 million tons per annum online. Something's going to happen in 2026. Notice we're going to bring 53.7 million tons per annum additional liquefaction capacity online. That's 58% will be coming from the US, 42% will be coming from Qatar. When you look at that amount of increase in supply, there's some pretty serious concerns that the LNG market is going to suffer a pricing consequence as a result of the oversupply. Which brings me to this quote from Gas Tech. And this comes from the CEO of Total Energies. The US is building too many liquefied natural gas plants. Patrick Poyan said on Tuesday, warning it could lead to a long-lasting glut in the market if all planned projects come online. We are building too much, he said during a panel on LNG and gas tech conference in Milan. We are facing many US projects. We will face oversupply for some years if all these projects come on stream. The thing that's interesting about this quote is Total Energies decided to go in on the next decade Train 4, but they declined to invest in the next decade Train 5, which they just made FID on recently. Now, let's take a look. The whole reason why you guys are here is to have an understanding of, well, you know, what baseload liquefaction technology options are we using in the US? And so before we look at this content, let's take another poll. How much power does an LNG facility consume per million ton per annum produced? And you guys are, these are just very rough numbers, but it'll give you a really good idea of the amount of horsepower, if you will, required to make LNG. All right, let's see what we have. Notice 9% said 30,000 horsepower. 26% said 60,000 horsepower. 43% said 100,000 horsepower, and 22% said 120,000 horsepower. As far as making 1 million ton per annum, roughly it takes 60,000 horsepower per million ton per annum. And you guys, that is a very rough number, but it gives you an appreciation for the size and scale of these facilities. So some baseload statistics. Notice baseload liquefaction plant could be anywhere from 1 to 8 million tons per annum. As far as our construction, we go from modular trains, which we're seeing used in Louisiana LNG, Stage 3, Corpus Christi, and the Venture Global plants, to mega trains, such as Qatar and the ones that Sabine Pass are considering. This requires a feed gas rate of roughly 140,000 standard cubic meters or 50,000 standard cubic foot per ton of LNG. 1 million ton per annum is roughly 4 million standard cubic meters per day, 143 million standard cubic feet per day of feed gas, roughly 45 megawatts and 60,000 horsepower. 5 million tons per annum is the 100,000. Actually, it's much more than that. Notice 5 million tons per annum, you need 300,000 horsepower to get that liquefaction plant to run, and 750 million standard cubic feet a day. So these are massive facilities. If we're going to be using gas turbines for our compressor drives, then you should expect to consume 7 to 8% of your feed gas, and that would be for a modern gas turbine. In terms of our long-term sales purchase agreements, you're looking at 20 to 25 years with extensions. As far as contract value, notice a 1 million ton per annum contract is valued more than 346 million US dollars, and that's assuming a $6 per million BTU purchase price. For those of you who are interested, the Department of Energy actually publishes our LNG export pricing here in the US. It's public information. And so that was pretty average a few months back. As far as capital costs, you're going to be looking to spend well over $1 billion per million ton per annum capacity. And one reference point would be the recent Venture Global 20 million ton per annum CP2 facility, which is quoted to be roughly $28 billion in CapEx. As far as these plants, notice I'm showing the block flow diagram. And really, when you look at these facilities, they're a very large gas plant with much tighter contaminant specifications on water, CO2, and H2S, but also on heavy hydrocarbons, because heavy hydrocarbons will freeze at the very cold temperatures that we need to get to in the liquefaction facility. And so in many regards, it really is very much like gas plant operations, just larger scale and tighter specifications and much colder, much more powerful refrigeration. So the first process that I want to talk about is the Conocophillips optimized Cascade. And this technology is being utilized at Cheniere Sabine Pass and Corpus Christi trains 1 and 2. I have this great video that I would like to share, and given the delay in my computer, I'm not sure if it's going to run. I'm going to go ahead and try it. If it doesn't pan out for us, then we will just carry on. All right. I just love that video because it really puts into perspective the size and scale of these facilities that we're putting on the ground. And I think it also helps you appreciate um, why the capital cost is so significant. And so, come on, let's go. Uh, there we go. All right. So, in terms of these facilities, essentially, when you start talking about liquefaction, it's nothing more than a ginormous refrigeration plant. This gives you an idea of a chiller energy balance, and this would be an example using pure component refrigerants. And so you can see here, we have our natural gas coming in. So here's my feed gas coming in at 40 C or 100 Fahrenheit, and then I leave at minus 160 C or minus 260 F. As far as the way this liquefaction uh, plant works is I'm taking high pressure liquid refrigerant, I'm letting it down, I'm boiling a whole bunch of refrigerant in different type of heat transfer equipment, and then I take all of that low pressure vapor and I compress it back up and run it back into a loop. For for the Cascade refrigeration, um, basically what the Conocophillips technology uses is we're going to use one refrigerant to condense another refrigerant, which will boil at a colder temperature. And so I'm getting refrigeration at multiple levels. And this is typically used in ethylene plants and LNG processes. You typically would not see Cascade type refrigeration deployed in a natural gas processing plant. Now, this gives you an idea of the flow sheet for an optimized Cascade process. Notice my feed gas comes in, and the first refrigeration cycle that we see is the propane refrigerant system. And so my feed gas goes through the propane refrigeration unit. And notice I'm also taking my ethylene, high pressure ethylene gas, and I am condensing the ethylene in the propane system. And I also have an open loop methane refrigeration circuit, and we're pre-cooling the methane loop in here as well. The streams leaving the propane refrigeration unit exits at roughly minus 30 Fahrenheit. And so you can see my methane carries on into the methane cold box. My natural gas, which is the blue stream, goes into the ethylene refrigeration unit. And now I have my ethylene condensed refrigerant being supplied to the ethylene cold box, where we now boil this ethylene, and I will get both the methane refrigerant and my feed gas, which is LNG at this point, to roughly minus 130 to minus 150 F. Notice from here we go into the methane cold box, and that is where all the proprietary information resides for the optimized ConocoPhillips Cascade process. And out from this methane cold box, we have our LNG rundown stream leaving at minus 245 Fahrenheit. We then go into our storage tanks at minus 260 F. I apologize for folks if anyone dialed in from overseas. I did make this presentation FPS dominant, so apologies for that. In terms of the optimized cascade, notice we're using pure refrigerant. So a pure refrigerant boils at a constant temperature for a given pressure. But basically what's happening is my methane open loop refrigeration unit is rejecting its heat to the ethylene refrigeration system, which then is rejecting its heat to the propane refrigeration unit. And here, that propane refrigeration unit, the final heat sink going to atmosphere are all those propane condensers. And so that's why when you look at photos of those facilities, or you saw the video of the Corpus Christi trains, there's literally hundreds of propane air condensers, because that's the final heat sink that is ejecting all of the heat that's being removed from the natural gas that's being liquefied, but also all of the energy that's being put into the refrigerants from the compressors. Now, as far as the heat transfer equipment that is used in the ConocoPhillips optimized Cascade, the propane and ethylene refrigeration units use core and kettle heat exchangers. And basically, these are large heat exchangers where we have a big pressure vessel where we're boiling the pure component refrigerants. And inside of these vessels, we have brazed aluminum cores where the feed gas, the ethylene, and the methane refrigerants are flowing through depending on where we are in the facility. Notice we get much tighter temperature approaches with a core and kettle heat exchanger than we could achieve with a shell and tube heat exchanger. As far as the methane and ethylene system, we also have some economizers, which everyone that is familiar with cryogenic gas plant operations, they're brazed aluminum heat exchangers. And we put all this equipment, including some flash vessels and control valves, inside a cold box. And so when you looked at the video and you saw that big box going through the facility, that would have been one of the cold boxes used in the liquefaction trains. Now, the other technology that we have deployed in the US is the APCI C3MR. And so that's Air Products and Chemicals Incorporated Propane Pre-Cooled Mixed Refrigerant. The liquefaction trains that will be using this, or that either use or will be using this technology, include Freeport, Cameron, Lake Charles, Golden Pass, and Next Decade. Now, the difference with this APCI C3MR is now we're going to deploy a mixed refrigerant. And so when we have multi-component refrigeration, basically what we're doing is we're making a refrigerant out of different compositions. And so these compositions obviously have different boiling points. And the way this works is that the lowest temperature boiling components, for example, nitrogen, methane, they're going to evaporate before the higher temperature boiling components do. And so if I were to boil this mixed refrigerant at constant pressure, notice if I'm boiling this one at 100 PSIA, you can see I'm going to start boiling at minus 263, which is a really convenient boiling temperature if I'm trying to make LNG. And you can see as that refrigerant continues to boil, my composition changes from light ends boiling off to heavier and heavier and heavier. The refrigerant actually boils at warmer temperatures as that as the mixture sits inside those heat exchangers and boils off. And so basically this process continues until the last heavy components evaporate. Now, this gives you an idea of the APCI C3MR LNG process. Notice the whole front end is just like a gas plant. I have acid gas removal. Then I go through MOLSIP dryers, and notice we're using propane refrigeration chillers, gas chillers here to, in this case, I'm reducing the water load going into my MOLSIP dryer. And then we're going to get this gas even colder. This would be an older type design where we're going to have the heavies removal column not integrated into the main cryogenic heat exchanger, which is this big coil wound heat exchanger at the bottom here. We go through another propane pre-cooler. And you can see for this plant, we're taking the heavies that we've removed from the natural gas and sending them into a fractionation train. Now, I will only do that if I have sufficient NGLs in the inlet gas to justify a fractionation train. But the key point here is notice we need to have these compositions available to us to make up our mixed refrigerant composition. This down here shows you the propane pre-cooling system. So in this example, we have 3 stages of propane pre-cooling. And then lastly, we get to the mixed refrigerant system. And this mixed refrigerant system is what's supplying the spiral wound heat exchanger. Now, we'll take a look at how this process works in more detail, but at a high level on the spiral wound heat exchanger, what you'll see is that all of my hot fluids are flowing up. And so my natural gas is flowing upwards. My mixed refrigerant liquids are being subcooled in a coil flowing upwards. I also have my mixed refrigerant vapors, my light mixed refrigerant vapors being condensed and subcooled. And then my cold fluids are downward flow. So essentially I'm raining my mixed refrigerant compositions down all these coils in this very large pressure vessel. And so if we look at how this equipment is fabricated, notice this gives you an idea of what those coils look like. So the natural gas and the various MR streams that are either being subcooled or condensed and subcooled will be flowing through these coils, and all those coil bundles are being installed in this very large pressure vessel. And this gives you an idea of what it looks like when we're transporting them. Now, let's talk about how this mixed refrigerant behaves in the main cryogenic heat exchanger. And so notice the first thing, I have my mixed refrigerant supply. I have a light mixed refrigerant and a heavy mixed refrigerant that is being produced from this mixed refrigerant separator. In this pass right here, I'm subcooling the heavy mixed refrigerant. And then in this other pass, the pink pass, is where I'm condensing my light mixed refrigerant. And in this coil over here is where my feed gas is coming in. I'm condensing and subcooling that feed gas into LNG. Now, you can see I have a JT valve. We rain our heavy mixed refrigerant down across the coil bundle, this lower warm bundle down here. This is an older design. Newer modern main cryogenic heat exchangers have 3 bundles, not 2. But at any rate, if we carry on and notice the light mixed refrigerant is being subcooled in the cold bundle up here, and my LNG carries on up into the cold bundle, and that is where I will be subcooling the LNG, from which I go through maybe a JT valve. This could be a liquid expander or something, but we need to have a way to let the pressure down to our final LNG storage tank. And so to give you an idea of the temperature and pressure profile in here, my natural gas could be coming in anywhere from, say, 580 to 725 PSIA, 40 to 50 bar, minus 32 C. I leave the warm bundle at 35 to 40 bar, maybe minus 80 C, or 500 to 580 PSIA and a minus 112. And then at the very top, I would be exiting 20 to 40 bar, minus 150 C. And then that'd be 290 to 580 pounds and minus 238 F. Some key points. First thing, the mixed refrigerant is condensing and cooling itself. And so it's kind of hard to get your head around that, but basically 70% of the main cryogenic heat exchanger duty is actually the MR circulation required to condense and cool itself. So really fascinating technology. It's really neat stuff. This gives you an idea of what the equipment looks like in the ground, on the ground. You can see the propane chillers are over here. There's the main cryogenic heat exchanger. There's the gas turbine exhaust. And notice again all the propane condensers that we have. As far as common drivers for these plants, this would give you an example of a frame 7 gas turbine, 85 megawatts, 114,000 horsepower. And so that's a common driver for an APCI C3 split MR design. This size is actually insufficient for the really large plants that Qatar has. In order to get this gas turbine started, notice I need a 20 megawatt or 27,000 horsepower electric motor added to my compressor string. So big equipment and a lot of power demand required for these facilities. Now notice, this gives you an idea of the cooling curves. So the green line is the cooling curve for my natural gas. That's where I'm coming in at say 30 C and I'm condensing my natural gas and I'm leaving at minus 160 C. The pure refrigerants here give you an idea of what the optimized Cascade process would look like in terms of thermal efficiency. And then the propane pre-cooled MR, see the MR is the blue line here. Now, you guys, this is a real high level schematic of what the thermal efficiencies look like for APCI versus optimized Conocophillips optimized Cascade. The optimized Cascade is actually much more efficient than what this diagram would portray, but you need to recognize that there's some significant differences between the two. The APCI, I have much less equipment required. I have a slightly better thermal efficiency because of keeping that mixed refrigerant composition to closely match my cooling curve. The ConocoPhillips has some advantages in terms of ease of startup on shutdown. I'll stay colder for longer. And also we can build in some operational flexibility. All right, so now that brings us to our friend, the Chart IPSMR technology. Now this is a modular mid-scale type liquefaction technology. This is being implemented at Corpus Christi Train 3. So this is the stage 3 expansion. Trains 1 through 7 have a net capacity of 10.5 million tons per annum. 8 through 9 will be 3 million tons per annum. What I failed to put on here was the new Fortress fast LNG that we have in the Gulf of Mexico. That liquefaction, those facilities are also using the Chart IPSMR. Now, as far as how this technology works, basically the IPSMR stands for Integrated Pre-Cooled Single Mixed Refrigerant. And excuse me, this is very similar technology that is being used in the BakerHughes Venture Global trains. And the max size for these types of trains might be roughly 2 million tons per annum. Now, notice in this type of lineup, we have our heavy hydrocarbon cold box. We need to remove the heavy hydrocarbons first. You can see we have our mixed refrigerant compressor and circuit, and then we also have an LNG cold box. Now, when we put all these pieces together and look at the type of equipment, when you look at this heavy hydrocarbon cold box, notice if you zoom in, we could use expander compressors. This looks very much like a cryogenic gas plant that you would expect to see anywhere else, other than we have a different way of doing the reboiling down here, for example, because I'm actually using hot gas to stabilize the NGLs that are leaving. So first thing, we have a heavy hydrocarbon cold box. You can see we're using a brazed aluminum heat exchanger here to do all of the heat transfer, and here is the mass transfer column. Here's the reflux drum and reflux pump. As far as the MR compressor, notice this is a two-stage machine, and we have a number of interstages. We'll talk about how this MR refrigerant works here in a moment. But this MR compressor provides all the cooling that we need for the liquefaction cold box. Now, as far as how this mixed refrigerant works, I'm going to start at the bottom here. And so notice this is my very light mixed refrigerant. And essentially we're boiling our mixed refrigerant compositions as we move up this pass in the brazed aluminum core. And here's my combined mixed refrigerant composition going into the suction drum. I go through my first stage of compression. I have an interstage cooler, and now I have my interstage knockout drum. Now you can see I have a very heavy mixed refrigerant being produced in this interstage knockout drum. And this mixed refrigerant is going to give us the warmest boiling temperature in the mixed refrigerant composition that we have. This mixed refrigerant is fed into the top pass here. I'm subcooling it, and then I'm boiling this heavy mixed refrigerant up in this pass right here. Now, if we follow the lighter mixed refrigerant composition on, notice we go through a second stage of compression, go through a discharge cooler or condenser, and here is my mixed refrigerant separator. I have my light mixed refrigerant that's coming out of the top and another intermediate heavy mixed refrigerant coming out of the bottom. This liquid mixed refrigerant is being subcooled. I feed it down lower into the cold box. These right here are standpipes. The purpose for these vessels is to provide even vapor and liquid distribution to the cores here. And you can see we bring this lighter heavy mixed refrigerant composition in lower into the brazed aluminum heat exchanger to give us a colder boiling temperature profile. And then lastly, we follow our very light mixed refrigerant, and that mixed refrigerant is being condensed and subcooled in this pass. And we separate out that light mixed refrigerant, vapor, and liquid from that JT valve, and we boil at the coldest temperature at the bottom now and flowing up. So you can see my feed gas is coming in warm at the top, and I exit as LNG out the bottom. And so the flow distribution is completely different than what we had in the APCI C3MR. In this instance, my hot fluids are flowing downward flow. And so that includes my natural gas, my MR liquids that are being subcooled, my MR vapors that are being condensed and subcooled, and all of my cold fluids, which are my mixed refrigerants, are boiling upwards. And so just a different lineup, but that gives you an idea of how the Chart IPSMR technology works. As far as these brazed aluminum cores, they're just a little bit more complex than what you would expect to find in a gas subcooled expander plant process, if you will. Now, as far as the last technology that we have to discuss is we have our BakerHughes NMBL technology. And this is what Venture Global is utilizing, and so is the Woodside, Louisiana LNG, and Commonwealth LNG. Again, this is a single mixed refrigerant technology, and Parker advised that on that last video, you guys were unable to hear my my audio on the video. So hopefully I got that fixed. So we'll see if this one works. So as far as this BakerHughes NMBL technology, modular technology, capacity 0.8 to 2 million tons per annum, we can use a power island, which can be utilized for an ELNG plant. It's pre-constructed turnkey modules, and so what the idea is that your final installation could be 15 to 20% faster. In this market, if we can get our liquefaction capacity online and to market 15 to 20% faster, that can give you pretty significant competitive advantage, which I think for those of you who've been following things, you've seen Venture Global do. Now, let's take a look at how this technology works. Yeah, Parker says that there's still no audio. I think that's okay. I don't think that I think all of the things are animated. So just read the screen. All right. So that gives you an idea of what the modules look like. In terms of additional details, you can see here's the process module. So that's everything included on this block one. So that includes my air coolers, vessels, the electrical control cabins, separators, and scrubbers. Over here, you can see the MR compressor. They can use an electric motor, or we could also use gas turbines. Just depends on, what your preference would be. In terms of the storage vessel, you can see this tall guy right here is the mixed refrigerant surge vessel or storage vessel. On the back end, you see is the brazed aluminum heat exchanger, the LNG cold box. And then on the back end is our E-room or soft starter. And so with that, you guys, it seems as if I cruised right through that conversation. So uh, if there's any questions, I would be more than happy to answer or have further discussion on anything that you guys would like to ask or know about. And again, apologize for I don't know what the thing was with my computer this morning. Apparently it didn't have enough coffee. I'm sorry. All right, quiet group. I'm happy to talk more details about any of the technology if you guys are curious. Will you be receiving the slides? Yes, we can email out a PDF of the slides for those of you who would be interested in having those. And yes, there will be a recording available. All right. Thank you, Alfredo. We'll be sure that we get you the PDF of the slides, and Hussein Salahi as well for you. Thank you, Iskander.
All right, I think that might wrap it up. If there's any more questions, feel free to drop them now, but I think that concludes our webinar.
All right. Well, thank you, Parker.
All right, everyone, have a great day.
Yeah, thank you. Bye.